All right, let's get right into it. What if I told you that picking between two simple-sounding algorithms could mean the difference between your code working beautifully or crashing because it ran out of memory? Well, today, we're diving deep into BFS versus DFS. This is going to be the ultimate guide to knowing which one wins and when. So, picture this. You're standing at a single point in some huge, sprawling network. It could be a map of a city, a social network, maybe even the entire internet. You've got a destination in mind. Now, you have two basic strategies to start exploring from where you are. And trust me, this choice isn't just for a textbook, it has massive real-world consequences. So, which way do you go? To answer that question, we gotta meet our two contenders, breadth-first search, which we'll call BFS, and depth-first search, or DFS. These two are like the foundational ways to explore graphs and trees. And believe me, their whole philosophy on how to get things done couldn't be more different. This slide just nails their personalities, doesn't it? BFS is super methodical. It's the patient one. It spreads out cautiously, one layer at a time, making absolutely sure it finds the closest things first. Seriously, the ripple in a pond analogy is perfect. DFS, on the other hand, it's relentless. It's all in. It just picks a path and goes for it, diving as deep as it possibly can until it hits a wall. Only then does it back up and try another route. So how in the world do they achieve these completely opposite search styles? Well, the secret isn't some kind of complicated magic. Nope. It's all about the data structure they use to keep track of where to go next. Let's pop the hood and take a look. First step is our Patient Explorer BFS. The official definition is exactly what it sounds like. It explores level by level by level. It'll visit every single node at distance 1 from the start, then all the nodes at distance 2, and so on. The super systematic approach, that's its superpower. So how does it pull this off? The secret sauce is the queue. A queue is what we call first in, first out, or FIFO. It's like a line at the grocery store. By adding your starting node, then taking it out and adding all of its neighbors to the back of the line, you literally guarantee that you'll process that entire first level of neighbors before you ever get to the second. It's such a simple, elegant way to get a really powerful result. Okay, now for its counterpart, DFS. The strategy here is the polar opposite. It is all about depth. The goal is to go as far as you possibly can down a single path. Once you hit a dead end, you backtrack just enough to try the next available turn. That's it. And the engine for this deep dive is a stack. A stack is last in, first out, or LIFO. Think of it like a stack of plates. When you visit a node, you push its neighbor onto the top of the stack. So the very next node you visit is the one you just pushed, the most recent one. This is what forces the algorithm to just keep digging deeper and deeper. When it hits that dead end, it just pops from the stack, which is basically backtracking. This is often done with recursion, which kind of uses the program's own call stack to do the exact same thing. Okay, so they have totally different strategies. One has to be faster, right? Well, when we get into the actual performance analysis, the answer might just surprise you. And here it is. In terms of worst-case time complexity, it's a dead heat, a total tie. Both algorithms in the worst case have to touch every single vertex, that's V, and every single edge, that's E, to finish their job. So they both run in what we call linear time, or O of V plus E. And that right there is the million-dollar question. If they're equally fast, at least in the big O sense, why do we even have two of them? Where is the real competition between them? Because the crucial point, the whole showdown, it's not about speed at all. It's about space. It's about memory. How much memory do these algorithms chew up? And as it turns out, that depends completely on the shape of the graph you're looking at. Here's the trade-off in a nutshell. For BFS, that queue can get gigantic if your graph is really wide and shallow. Just imagine a social media star with millions of followers. The queue has to hold all of them at once. But for DFS, the stack only grows with the depth of the search. So on a very deep but narrow graph, like a long linked list, DFS can get into trouble, maybe even causing a stack overflow if you're using recursion. And now we get to the main event. Now that we know how they work and their big trade-offs, let's put them head-to-head in some real-world problems. When do you actually pick one over the other? This table lays it all out pretty clearly. If you need to find the shortest path in an unweighted graph, think the fewest stops on a subway line, BFS is the undisputed champion. It's guaranteed to find it because of that level-by-level approach. But for something that depends on finishing one path before another, like a topological sort for scheduling tasks, DFS is your go-to. And, like we just said, on a really wide graph, DFS is usually going to be way friendlier on your memory.
It's worth pausing on this for a second because this is easily the #1 most common mistake people make. DFS might stumble upon the shortest path, but that would be pure luck. It makes absolutely no guarantee. It will happily wander down some long, winding path to a node, even if a shortcut was right there. If you need the shortest path, you have to use BFS. End of story. So let's bring this all home. How do you take all this knowledge and use it to absolutely nail a technical interview? It's not just about spitting out facts. It's about showing you understand the trade-offs. Here are your key talking points, your cheat sheet. First, say it with confidence. BFS finds the shortest, unweighted path. Second, clearly explain that memory trade-off. BFS struggles on wide graphs, DFS on deep ones. Third, when you get a problem, justify your choice based on these properties. And hey, for bonus points, you can mention that using an iterative DFS with your own stack can get around those pesky recursion limits on super deep graphs. That shows you're thinking about real-world code.
And really, it all comes down to this. There is no single better algorithm here. There is only the right tool for the specific job you're trying to do. Is your goal probably near the start? Are you looking for the absolute shortest route? Or are you exploring some deep, tangled structure? The expert knows how to choose, and now you do too.